Are you able to see the PPT?
Yes, sir.
Okay. So yesterday we started discussing groundwater. We discussed what is a groundwater, types of aquifers, confined and unconfined we discussed, and stratification also we have discussed. Okay, so today we'll begin with aquifer properties. So if you want to separate out aquifers from aquifers, this properties basically distinguish or compares the different aquifers. The first property is porosity. I think all of you are aware what is a porosity. The porosity is nothing but the ratio of volume of voids to the total volume of aquifer materials, or you can say volume of voids to volume of solids. That will give you the porosity. So every aquifer consists of different soil materials. If it is a different soil materials, then it will have its own porosity. Means porosity also is going to change, and it's nothing but a measure of water bearing capacity of the formation. Water can be available for the users. It can store more quantity of water. And but okay, so one thing it is there, like if the aquifer is holding some quantity of water, if you drill a well and if you pump the water, you will not able to extract all the water. Some water the aquifer will held back. It depends on the soil properties. Like clay soils, it will hold the water, it will not allow water to release. So the water that is held, we call it as specific retention, that contributes towards the specific retention, and water that we can pump out, that comes as a specific yield. So your porosity, you can say it's a sum of specific retention plus specific yield. Now let's discuss the another important property is specific yield. So whenever we drill a borehole, we always say, like if you ask what is the yield you are getting from the borehole, so what exactly is that yield? So that yield is nothing but the actual volume of water that can be extracted by the force of gravity from a unit volume of aquifer material known as specific yield. So when you drill a borewell into your aquifer, the actual volume of water that you can extract by the force of gravity. Okay, here, okay, and from a unit volume of aquifer material is known as specific yield. The fraction of water which held back in the aquifer is known as specific retention. So if you just consider a best example to understand specific yield is consider the sponge. Okay, I think all of you are aware what is a sponge. Sponge is a best description of aquifer it can give you. So you take a sponge, dip it in the water and just keep it. So when you dip it in the water, what happens? All the pores that is present in your sponge gets filled with the water. Now when you lift that sponge, what will happen? Some quantity of water will fall down by the force of gravity. Correct? The quantity that is falling down from that sponge due to gravity is the specific yield of that sponge. The same way your aquifer also behaves. So if the aquifer is completely saturated, and if you just take a piece, just imagine if you take a piece of that soil material filled and just hold it, water that can flow out due to the gravity is nothing but is your specific yield. The water which doesn't flow by gravity, which is there in the soil, it will held back by the soil, that we call it as specific retention. So when you drill a bore well, the water that can flow due to gravity, that much water only we can extract. It's clear what is specific yield?
Yes, sir.
Okay. Now different formations or different soil stratas or different aquifers consisting of this soil strata or formed due to this soil strata, their porosity and specific yield are mentioned here. Just hold on, whether I'll see whether I started recording or not. Yeah, it's recording. Hmm. So for clay, I told you clay has the highest porosity, 45 to 55%. But the property of clay is that it holds the water. That means you will have maximum retention there. The specific retention what we have spoken here, specific retention, or here that specific retention SR is highest in the clay. So, and the water which can flow due to gravity is very low. So that is why the specific yield, if you aquifer consisting of clay material, will be very less. So if you drill a bore well into this aquifer, you will get very less water. Well, if you go for sand, sand has a porosity of 35 to 40%, and it holds very less water. Most of the water it releases. So that is why you have specific yield ranging from 10 to 30%. So you get a good quantity of water. If it is a gravel, you have a much better specific yield. Sandstone has 5 to 15%, shale 0.5 to 5, limestone 0.5 to 5%. So these are the generalized values of different formations. Now if we just let's discuss another property, that is the storage coefficient. We also call that as a storativity. Now if we just consider your aquifer material 1 meter by 1 meter cross section. So suppose this is your so consider a aquifer with unit surface area, so 1 meter by 1 meter. Now if it is having water, consider the water is at this level. I'll mark with another color. Suppose this is the level of water at present. Now if I am pumping the water from here, what will happen? I have drilled bore wells, consider, and I am pumping the water some quantity. Then what will happen? The water level will fall down. So I will pump till the water level falls down by 1 meter. That means suppose this is the new water level, and the difference between the new water level is 1 meter. So the quantity of water I have pumped till the water level drops down by 1 meter is nothing but my storage coefficient or storativity. That means it's the quantity of water or volume of water that can be extracted from the your aquifer if the water level falls down by 1 meter. Same happens with the recharge. If the water level is here, if I am recharging, the quantity of water required to raise the water level by 1 meter is also storage coefficient. Both the quantities will be same. So that is what it's mentioned here, the volume of water that an aquifer releases from or takes into storage per unit surface area of aquifer per unit change in the component of the head normal to that surface. So in the 1 meter change in the water table, how much water it can release or how much water it can take considering the unit surface area of aquifer is your storage coefficient or storativity. Clear? What is the storativity?
Yes, sir.
Now there is another property of aquifer is transmissibility. So transmissibility we call it as T. So this we apply after considering the aquifer of unit width and thickness B. Consider an aquifer whose width is 1 meter and thickness is equal to B. So that is the depth of fully saturated zone. So if you consider your confined aquifer from here to here, what is the thickness of your aquifer will be your B. And for unconfined aquifer, normally we consider from the water table level to the bottom impermeable level, that will be the my thickness B. So that is nothing but a thickness of your saturated zone. So if you consider that the discharge through this aquifer under the unit hydraulic gradient, that is equal to T is equal to K into B. So if you just consider a system, so this is my bottom and this is my groundwater level, this is my impermeable layer here. So at this the thickness, this basically will give you the B, and the discharge, what is mentioned, the discharge to the aquifer under the unit hydraulic gradient. That means if my water level, means you can just say the slope of this line is 1 by 1. That means if I move by 1 meter, my water level is also falling down by 1 meter. That is called as unit hydraulic gradient. So if these conditions are there, then the discharge through the aquifer is equal to T is equal to K into B. So this particular term we call it as transmissibility of that aquifer. So this basically tells how much quantity of water is moving, basically it can transmit, and it has a dimension of L square by T. So this also you should remember, though it is a, we call it discharge, but since we are using unit width, its unit becomes, instead of L cube by T, it becomes L square by T. So normally we write as a meter square per day or meter square per second, etc. So if you want to define, you can define in this way. The coefficient transmissibility may be defined as the rate of flow of water in meter cube per day through a vertical strip 1 meter wide, extending the full height of the saturated thickness of aquifer under a hydraulic gradient of 1 meter per meter at a prevailing temperature. Here why we mention meter cube per day, because here we are mentioning vertical strip 1 meter wide. Okay, so this is what the transmissibility of an aquifer we can define. So this is a numerical. We'll do this numerical in the next class. We'll first finish the theory and then we'll start this numerical. So another important thing that we consider for groundwater is the Darcy's law. So we always consider, I think you might have studied what is the Darcy's law, and we consider the Darcy's law is valid for groundwater flow. So it has been proved that Darcy's law is valid for the groundwater flow. So that is why when you want to calculate the groundwater flow, we always apply the Darcy's law. What basically Darcy's law, it says V is equal to K into I. So where K is the permeability or hydraulic conductivity, we can say, of the particular soil, and I is the nothing but we call it as a hydraulic gradient. That means in a term we say minus dH by ds, that is the drop in the groundwater table with respect to the distance. Since the water table is dropping, we represent this with a negative sign, and here H we call as a piezometric head is nothing but your groundwater level, and S is the distance measured in the general flow direction. The negative sign emphasizes that the piezometer head is drops in the direction of flow. So I think you are aware of what is this Darcy's law. V is equal to K into I. So this is what we apply in the groundwater system. So if we just consider, if this is my ground strata, impermeable strata over which my groundwater is there, and this is my groundwater level. The slope of this line is nothing but my dH by ds, and since it is dropping, this will be negative. And if I know the permeability of this particular soil, the velocity at which the water is moving is V is equal to K into I. If you want to write in terms of Q, so Q is equal to A into V. So if you substitute V here, so your Q is equal to V is equal to Ki and then A. So Q is equal to Ki A. So that's how we calculate the discharge through the groundwater system if you know the area. So and I can write in this form minus delta H by delta S. So minus where minus delta H is the drop in the hydraulic grade line. So that is the drop of this particular line. So you can say that basically the slope of this particular line will give the delta H by delta S. Okay, clear? The aquifer properties. Anyone has any doubts?
No, sir.
Okay. So these properties you should study it. Small questions can come, like explain transmissibility or explain the specific yield or storage coefficient. You should able to write. And also in this session you should study about okay, stratifications also sometimes numerical can come. Theory part you can study what is confined, unconfined aquifer and the types of water bearing layers. Okay, now let's move to the next part of groundwater, that is well hydraulics we will study, and in the next class we are going to do the numerical on groundwater hydrology. I'll share the next slide. Are you able to see the next lecture number 28?
No, sir.
No.
Yes, sir.
It's coming now? Okay.
Yes, sir.
Yes, sir.
Okay. So this particular session is basically we are discussing in this session is the well hydraulics. So normally if you just say groundwater, how do we extract the groundwater? By digging a well. So earlier people used to dig open wells, but that the depth of those wells is very shallow. So nowadays everyone digs the bore well and we pump the water from it. So that is why this well hydraulics plays an important role or important. It becomes an important topic to understand. It's easy. So there are some couple of equations. First, to understand what exactly happens when we pump the water from the bore well, and there are some couple of equations for confined and unconfined aquifers. Those you should remember. So well hydraulics is nothing but to understand the process in effect when one or more wells are pumping from an aquifer. So in an aquifer there will be multiple wells. So if those wells pump, or if one well pumps, what is its effect on the other well, or if multiple well pumps, what is its effect on the surrounding. All those things it can be described using the well hydraulics. So why it is important? Because the groundwater withdrawal from the aquifer are important to meet the water demand. Therefore we need to understand the well hydraulics to design a pumping strategy. So basically, to design a scientific pumping strategy, we should have a basic knowledge about the well hydraulics, and we should able to say that this much quantity of water we should pump, or this much quantity of water is safe to pump basically. So if you want to guide any agriculturalist or anything which they dependent on the bore well for the water extraction, so we should able to tell this much quantity of water we should able to extract safely, and based on that he can decide what crops he should be growing. So there are myths basically in the like with the people that groundwater is the infinite source of water, but that's not true. Just like how we store the water in our overhead tank, same way the water gets stored in the groundwater, and it has also has a limited quantity just like the overhead tank. So when you extract more, then you get, and if you are basically if your recharge rate is lesser than your extraction rate, then what happens? Your groundwater starts getting exploited, water level starts falling down, and after some time you will not able to extract sufficient quantity of groundwater. So this I think you are aware. The well system usually have your well, pump, and the discharge pipe, and the well usually consists of a perforated casing. So normally to prevent the collapse of well, we provide a casing, and that also we provide a perforated casing. So perforated casing means the casing with the small holes in it. That's we call perforation, so that it allows the water to enter into the well, but prevents the collapse of the hole. When the water is withdrawn, here the spelling mistake, water is withdrawn, the flow becomes established, and flow established to compensate the withdrawal. When you extract the water from the well, then what happens? When you suddenly extract, then the aquifer suddenly tries to contribute to that flow, and the water will start moving. And because of the head loss, the piezometric surface adjacent to the well also gets depressed. This is called a cone of depression. This I'll explain it in the next slide. Basically, it follows nothing but a Darcy's law. So what are the basic assumptions in the well hydraulics? Is that the piezometric surface of the aquifer is horizontal prior to the start of the pumping. That means the water level in the bore well is perfectly horizontal before pumping. The aquifer is homogeneous and isotropic. So it consists of same material and it has the same properties in all the direction. All flow is radial towards the well. That means the water is coming from all the 360 degree of the well, from the 360 degree of the well into the your well. So that's we call the radial flow. And we can also consider the groundwater flow is horizontal. Darcy's law is valid, and the pumping well fully penetrates the aquifer. These are the assumptions that lies in the derivation of equations for well hydraulics. Then what is a steady and what is unsteady or transient flow? Steady state basically implies that the drawdown is a function of only location. So when the drawdown is a function of only location, we call it as a steady state. When the drawdown is a function of location and time, then we call it as a transient state or unsteady state. So in our syllabus, we are going to study on the steady radial flow or steady state flows, and we are not focusing on the transient or unsteady flow in our syllabus for you, because this is at the advanced level, and when you take there is a separate electives, or when you go for a master, we will have a separate subject on groundwater hydrology. There you will be studying detailed about the unsteady flows. So here, just to give an introduction or give a sufficient idea, we are focusing on a steady flow. So now we'll first discuss with respect to the confined aquifer system. So this is basically the steady radial flow into a well in a confined aquifer. Now you consider a confined aquifer. So this you can see is a confined aquifer. So this is the top confining layer. This is the bottom confining layer. The depth of this is B. You can see we have drilled a bore well here. What you can see dotted lines, those are the perforated casings. And before pumping, our water level was at this particular level. So what level you can see? It is at this level before pumping. The radius of this well is RW. So that means the diameter is 2 times RW. So total water depth from the bottom of the aquifer, you should remember this is from the bottom of the aquifer, is H. So with this, once we start the pumping, what will happen? The water that got stored into this well starts coming out, and there will be drop in the water level in the bore well. Once this water level starts dropping, then what happens? This aquifer from all the 360 degrees, that is the radial flow, will get established, and the aquifer's water will start rushing towards the well. And then the equilibrium it reaches, and it will get, if you maintain a uniform discharge, it will get steady at one particular level. So consider this level is a steady level after some time. So you have started pumping of the water level started falling down, and at this particular level it becomes steady. That means the equilibrium has reached. The water that is coming out, same water, the aquifer is supplying to the well. So that is why this level is maintained. Now what you have identified, what your observation says, you're observing, you can see this depression we can see here, and here means basically it will on all 360 degrees you will see a depression like this. We call this as a cone of depression. Now if you have an adjacent well here, suppose at this particular location, maybe at a location R1 from your bore well, center of your bore well, if you another well, the water level in this well also will fall down to this particular level. So the effect of pumping is seen in at this particular point. If you have your bore well is here, another bore well, then at this bore well your water table will be at this particular level due to the pumping from this bore well. And at certain distance, the effect of this bore well gets diminished. Means at this particular level or at this particular level you can see. After that, if we pump also, there is no change in the ground water. So this particular zone where it can affect, we call it as the zone of influence. Like from here to here, will be your zone of influence of this particular well. So when the pumping starts, this much diameter around the well will have the effect. Or you can say, if you measuring from center, so this much radius, it's going to influence. We also call it the radius of influence. If you are measuring from the center, so from here till here, it will be my radius of influence. So that's, I can say it as capital R. So this value what it is shown here is nothing but the radius of influence. Now here what H values we are seeing, we call it as a piezometric head. That means the depth of water, and we measure from the water level to the bottom, that means to the impermeable layer. Normally when you are measuring the groundwater, we measure from the top. We are not sure of what is basically these levels, and difficult to estimate. If we know the total depth of this thing, the saturated zone, what we can measure from the top is the S1 and S2, or S values what we are mentioned here. So those S values are nothing but my draw down. So draw down, and this you can calculate. This you can measure from the here. From here you can calculate H1 or H2. Basically, your H minus S1 will give you H1. H minus S2 will give you H2. Or H1 plus S1 is H, like that. So normally these values we can measure. So with that, we can calculate what are my H1 and H2 value, provided you know the total thickness of your saturated media. Okay, so this part is clear, what exactly happens. Now we'll start discussing the derivation. Anyone has any doubt in understanding this part?
No, sir.
So it's clear. Now if you want to estimate the Q, what is being done is we apply the, what I explained is given here. So if you want to explain, if you want to derive the equation, the first thing what we do is apply the Darcy's law. So you can see the Darcy's law is applied. Q is equal to A into Q. So area is, its RW is the, can see its radius. So area you can calculate 2 pi RB minus K dou H by dou R. And if you simplify these equations, we come up with an final equation. So no, don't worry about the derivation part. You should remember what is the equation, what equation we should be using it for our problem. This is for the confined aquifer. So final equation what we can get, we call it as a Thin's equation. So here your T is equal to, that is T is nothing but a transmissibility, that is K into the thickness of your aquifer B is equal to Q divided by 2 pi H2 minus H1. What is H2? What is H1? If we refer this figure, this is H2, this is H1. Into ln of R2 by R1. R2 is the distance of this borewell, consider H2 position from the center of my pumping borewell, and R1 is the distance of H1 from the center of my pumping borewell. So if we have this data, so if you know what is the pumping rate, if you know what is your pumping rate, and if you in the surrounding borewells, if you know the levels in the water, levels of the groundwater level, then you can calculate the transmissibility of the aquifer. Or if you know the transmissibility of aquifer, you can calculate the discharge from the aquifer. If you know the borewell levels and their distance, we can say that okay, this is the rate at which the pumping well is pumping. So this you can also write in terms of Q. If we just rearrange, Q is equal to 2 pi T H2 minus H1 divided by ln of R2 by R1. Okay, so this, when you rearrange, you can write in terms of Q. Normally, what we measure is the drawdown from the ground level. So if you want to write this equation with respect to the drawdown, you can also write in this way, or can say where Q is equal to 2 pi T S1 minus S2 divided by ln of R2 by R1. Here we have written H2 minus H1, here it is S1 minus S2. So this value should be positive. We need basically the difference in that level. So when you go with respect to isometric head, you can see the farther distance the borewell have a higher head compared to here. So that is why we do H2 minus H1. But when you go for drawdown, you can say your S1 is higher than the S2. So that is why we write S1 minus S2. And you will get the value as positive value here. Okay, so this formula is clear for confined aquifer. So this you should remember. 1 second, to show one more thing. Hold on. Okay. Further, if you just consider at the edge, like here we calculated with respect to the bore wells, surrounding bore wells at a distance of R1 and R2. If we don't have those things, if we just consider this bore well, and if we just consider its just consider um, the zone of influence at the edge of the bore well. Like this is the center, and from here I'm considering this edge of the bore well. What is the distance basically from here to here is nothing but the radius of my bore well. So that is equal to RW. So if you consider at this particular level, and if you rewrite this equation, the same equation, you can write in the way, I'll write it here. Further, at the, can note it down. To the edge of the zone of the influence. what's basically happen? You draw down S is equal to 0. Your R2 will become equal to R. Your H2 will be H. If you just consider this one, your R1 will become RW. At this point, your R1 is become RW. H1 will is equal to HW, and S1 is equal to SW. You can rewrite your equation as Q is equal to 2 pi T SW divided by ln of capital R by RW. So what thing we have considered here is, we just go back to the figure. So we have considered from suppose you consider our one well is at the, here we have considered H1 and H2. So here H1, it becomes it is at the edge of my bore well, and H2 is at the end of my radius of influence. So this is R. So at the radius of influence, what is the thing? My drawdown is 0 at this point. My S is equal to 0. At this particular point, my S is equal to SW. My R1 will be equal to my radius of my well. So that is RW, and capital R is the radius of influence. So if you don't have the borewell data in between, I know what is my radius of influence. With that also I can calculate my discharge. So in that case, my equation will get reduced to this particular form. Same equation gets reduced to this particular form. So this also you should remember. Okay, got an idea? So once you do the numerical on this, you will able to understand these problems better. Any doubt? Is it clear?
Yes, sir.
Same way, you can derive the equation for unconfined aquifer. So here the base is impermeable and top water level is at the atmospheric pressure. It will have the same effect. What we think, once we pump the water from the borewell, we have a cone of depression, and then we will have the piezometric heads H1, H2. Other things, it remains the same, other notifications. And if we apply the Darcy's equation for unconfined aquifer, what equation we get is this equation. So Q is equal to pi K H2 square minus H1 square divided by ln of R2 by R1. So this equation, we use it for unconfined aquifer. So here basically the square term comes. You cannot replace it directly. You cannot write like with respect to S2 square, sorry, S1 square minus S2 square, because it's a square term. So what we need to, if you know the drawdown, we need to convert that drawdown into piezometric heads. So if you know the total depth of saturation minus the drawdown, you will get the piezometric heads, and which should put the value in terms of piezometric head for unconfined aquifer. Why this square term come? Because it H is nothing but that will be equal to your B here. So H is nothing but that will be equal to B. So in the confined aquifer, our equation was 2 pi K 2 pi T. The T is nothing but K into B. So here that K into B gets simplified into K into H, and that further when you solve this equation, we'll get the square terms here. Okay, so this is the equation we use it for unconfined aquifer. So you should remember the equations for confined and unconfined aquifers in the well hydraulics. So in the next class, we are going to do the numericals on it. Okay, so we'll stop here. If you have any doubts, you can ask. Otherwise, we'll end our class here. Let me download your attendance. Okay. So you guys are submitting the assignment today? Yes?
Yes, sir.
Okay.
Yes, sir.
Okay. So you mail it to my email ID. You know my email IDs, no? You mail it to my both the email IDs. Okay. Okay then. Thank you. So next class we are going through the numericals on groundwater hydrology.